Yeah.
Excellent. Good.
Good.
All right. So, everyone knows what we're here with us. Now we're going to John's MSR thesis presentation. John's been on for a couple of years, been doing lots of awesome stuff with lighting robots. I think holds the record for most being on most papers as an MSR student and all that, which is very impressive. It's been awesome having you around. Glad you're sticking around for a little bit more. So yeah, I guess we'll do hold questions during the talk pretty much, and then we'll do Q&A at the end. We'll do the committee first, and then pull it up for everybody else. Ground rules. Take it away, John.
All right. Thanks, guys, for coming. There are pastries if you are looking. But yeah, thanks everyone for coming. Talking about the Lego robots today. Thanks for my committee members, Zach, Guanya, for being here in person, and Deva and Kevin for joining remotely, despite your busy summer travel schedules, I'm sure. So I'm here talking about Lego robots. I thought I'd spend most of my master's working on contact optimization, optimal control, whatever. And then I looked at all my papers and I realized I should give a Lego robot talk today. The good news here is that it's actually really easy to motivate Lego robot talk in 2024. If you read the news or blog posts, these are supposed to be general purpose agents in the physical world. You combine these things with ChatGPT or some whatever AI we can throw on these systems, and we're supposed to revolutionize the workforce and our economy and so on and so forth. The market seems to believe that that's going to be the case. Boston Dynamics was sold a couple years ago for almost $1 billion. Figure AI is a humanoid startup company from the Bay Area, had a valuation of $2.6 billion. And more recently, just earlier this month, our very own Deepak Navnath startup, Skilled AI, raised $300 million at a $1.5 billion valuation from Series A alone. And you can kind of see, you can understand the excitement a little bit. These robots are finally doing really useful things in the wild. Here, the Spot robot is doing the inspection tasks in the power plant, and humanoids carrying heavy boxes in the warehouses. And in this case for Skilled AI, we have robots loading dishes, opening the fridge for people, and in this case, presumably, writing someone's thesis on their computer, which is my personal favorites. If you look carefully at some of the demos these companies are putting out, we're picking out Tesla today because Shuo is not here. Look at these. Remember, this is supposed to be the state-of-the-art, latest and greatest progress. Shuo and his friends are showing Elon their recent progress. Elon was excited and posted this video on Twitter. These are supposed to be, but if you look at compare this to what happened, what Honda did 20 years ago, it's really kind of fair to question how much progress do we actually make in this space. These robots are still, even in 2024, still walking really, really slowly. And my 82-year-old grandpa can probably walk upstairs faster than these robots walking on flat surfaces right now.
I think they're using exactly the same method. ZMP.
Yeah,
there's not even NPC there.
More
Yeah.
maybe offline conversation, but yeah.
Yeah.
I don't want to.
There's one that looks similar because they're using exactly the same method. Yeah.
Anyhow, but if you compared to what I showed you a slide ago, these are people and animals, and they're doing much more agile, athletic, dexterous things, all those stuff. And forget about robots. I wish I can do these things. But the point that I'm trying to make here is that despite all the excitement, the money flowing from industry, we still have a long way to go to reach this level of agility for these Lego systems. To get a sense for how these things work in general, at least in the model predictive control context, which is mainly what we're going to talk about today, let me walk you through a real world example. Here I have an Alice robot. I want my Alice robot to go fetch me that coin all the way over here, but there's a gap in the middle. So in general, what I have to do is tell my Alice robot, you're going to take off here and you're going to land over here. And once I have these the more difficult discrete flavor decisions made for my robots, now I can now can throw my favorite trajectory optimization algorithm at this problem, and it's able to generate these beautiful motions in between these discrete decisions that I make and complete this task. In the reinforcement learning case, it's a little bit different, but still you have to do some sort of hand-holding to make your system solve this problem. And the second part that's annoying about these things, right, is that these robots are have very high dimensions, And you have a lot of articulated bodies, a lot of joints, and also all that sort of stuff. And in the MPC case, this becomes very computationally expensive. And what people typically do, in at least historically, more so recently, so slightly different. But in general, you have to simplify these models to something that has much more lower dimensions, so you can compute these control policies in real time online. The dream, right, is that instead of the annoying hand holding I have to do for these robots, I would like my robots to just go watch some expert online and watch YouTube videos for a couple hours and then solve this task by itself instead of me hand hold and design rewards and all that kind of crap. And instead of these reduced order models, I would like my robot to use everything it knows about its own dynamics, all the degrees of freedom, and plan motions efficiently online. So with that said, here's the list of papers that I worked on during my master's. For today's talk, I'm primarily going to focus on SLoMo and ReLU-QP, but I'll briefly go over some of the content that's covered in fast contact implicit MPC and PPR, which we did with Deva for ICCV last year. The rest of the talk will be split into two parts. The first part I'll be covering SLoMo. This is where we're discussing the motion imitation problem from casual videos. Also, how can we take a video of a cat or a human and transfer the same motions onto robots. And the second part of the talk would be discussing how we leverage GPUs to accelerate whole body predictive control in real time. So the first part of the talk is on motion imitation, and the question everyone is asking in robotics these days is, where does the data come from? In the context of manipulation, this is a little bit well defined. It's much better defined. In this case, you can imagine build essentially a clone of the robot for the human operator to operate in and collect these data. So even in the manipulation context, the data problem is not solved by any means. For like a robot, this gets a little bit fuzzy. These systems have much higher degrees of freedoms. They have floating bodies, and designing teleoperation controller for these things are a little bit annoying because you can't just bolt the system on the floor and collect data that way. But Boston Dynamics a couple of years ago taught these robots to tear up the dance floor, right? So I think we can maybe use this as a case study and think about how they were to achieve this. Well, the first thing they did is hiring some professional choreographer and putting them in a very expensive motion capture studio. These are the motion capture studios you typically see on film sets, and they can collect human motion data, very high quality human motion data. And once they have the high quality human motion data, there's some animation expert that massage these trajectories into the robot configuration space. And once you have that, to put these things on hardware, you hire some controls engineer, robotics grad student. If you can't afford a real engineer, you have to make it takes a couple of days of tuning to make these things happen on hardware. And here you have, in this case, you have 3 working professionals working together to make a single demo happen. And clearly, this is probably not the way we're looking for to scale up robot data collection in these days. We're looking for large amounts of data. What can scale much more easily are RGB videos that you can, that are widely available on websites like YouTube. You can also easily acquire more data by just taking out your phone from your pocket and opening the camera app. Record your pet, doing something funny or whatever. This is, actually not a revolutionary idea by any means. In the context of learning manipulation policies, this was also work from CMU. They studied learning motion primitives from internet scale video data for manipulation. But so far, at least until we worked on these things at the beginning of my master's, this learning motion primitives from video data has not been studied in the context of Lego robots. With that in mind, we wanted to propose a very, very simple algorithm. This takes 3 steps. The first step is 3D reconstruction, given some video RGB images or RGB sequence. We're solving the reconstruction problem that synthesizes a physically plausible set of trajectories in the key point trajectory in the world frame. The key points here are the color dots you see on the right. Here, in a sense, we're solving, colors came out weird, which, I'm sorry, but so here, in this case, we're solving the data compression problem from the super high dimensional RGB images to the relatively lower dimensional robot trajectories that we're accustomed to working with in robotics. And the second step, we're solving, once we have the key point reference, we're solving the policy optimization problem, in this case, a contact implicit trajectory optimization problem with nonlinear robot dynamics, contact, and the friction cone constraints. And we define the cost function to closely track the reference, the video reference that we synthesize offline. To make this optimization problem a little bit easier, we're actually using a reduced order model in this case, where we just abstracting away the legs and just model the legs as point masses at the end effectors. And in the online control setting, we were solving essentially the same problem, the same contact implicit problem online in real time with linearized dynamics, linearized contact, and linearized friction cones. And note that here you can equivalent in the offline optimization and online control setting, you can equivalent do reinforcement learning and sim to real techniques and achieve the same results. But more details, you can find the journal paper that we published at TRO earlier this year. So this all seems really straightforward. Clearly, there's a catch somewhere in there. It turns out, somewhat unsurprisingly, the price we're paying. Yeah, go ahead. Yeah.
So the tracking error here is the whole body or like centroidal or like.
This is the model. Yeah, so we're using the same model for offline tri-job and online control. So this is the same, basically the single rigid body with point masses on the feet.
Single rigid body.
Single rigid body, yeah. So the centroidal model, but it's not a centroid model because
like the tracking for the legs is still pretty good, right? So are you considering?
Yeah, we're considering the inertial effects on the legs as well.
So you're not explicitly tracking the foot position.
I am tracking the foot positions, but I'm considering I'm throwing all the inertial effects on the legs into a point mass.
You
yeah.
consider foot, but then dynamically you do a centroidal single rigid body.
Sure, yeah.
Is that correct?
That's not really like I still have the point mass dynamics on my feet.
Okay.
Yeah.
I see.
But I'm just ignoring the kinematics in the legs. All I'm ignoring is the kinematics in the legs.
I see.
You have a slide on this?
No, but yeah, we can.
Just for trying to understand what is the tracking error you're trying to.
Yeah, so I have a video somewhere. It's basically looks like a plate with like ping pong balls with feet. Like it's
Gotcha.
if they can if you can picture that in your head.
I think, are you asking about the model or the cost function?
The cost function.
Yeah, can you describe that tracking cost?
The cost function is literally the square distance between like what we synthesize off, because this is the same. There's no model mismatch between these two stages.
Okay.
Yeah.
Gotcha.
Well, what is that function? What
It's
is
just-
the tracking error? Is it just body pose? Is it?
Yeah,
body pose and leg and like position.
Unlike positions in. So it's
Sorry,
not
feet position.
It's not in joint angles. But
Not in joint angles.
Okay, gotcha.
Any other questions? Okay, I think we'll keep going. Yeah, thanks for asking the clarifying questions. Please feel free to interrupt me during the talk. So perhaps somewhat unsurprisingly, the price we're paying with the cheap accessible video data is that we have to somehow deal with the fact that monocular vision is fundamentally ambiguous. Even if you just take the state-of-the-art reconstruction algorithm and throw it on these dynamic at these dynamic objects and scenes, you can get a bunch of really unphysical artifacts. Here, the cat is floating in the air, feet are sliding across the floor, and have severe ground penetration. In which all of these things are extremely scary if your goal is to put these motions on robots. And another example of this is from the visual evidence alone. This reconstruction looks really good, but if you look at it from a reference view, the center of mass actually projects outside the support polygon, so this is not physically at all. The sock should not be standing here. To fix some of these problems, we have to go back to the reconstruction stage for a second. This is a whole nother paper we did with Guanya and Deva. The key insight here is that instead of just minimizing the rendering loss in the kinematic reconstruction algorithm, what we're saying is by adding also minimizing over physics loss, by rolling out my reconstruction in a physics-based simulator or the robotics simulator that we all know and love, maybe. And it turns out we can reduce a lot of these infeasibilities. And then this new reconstruction with both the rendering and physics loss turns out to be much more useful for the downstream optimization and control tasks. So let's take a look at a couple results. We teased this a little bit earlier. Here the robot is mimicking a dog reaching for water, walking like a cat. And my personal favorite, doing CPR on a human partner. And what's cool about this is that we can still throw the exact same algorithm on the human to humanoid transfer problem. Here the robot is waving at the camera, stretching, probably got tired carrying boxes, and then doing jumping jacks. So SLoMo was kind of the first work thinking about how we can turn RGB videos into Lego robot control policies. There's been some later work that came out after earlier this year, specifically targeting human to humanoid motion transfer problem. One of them, the H2O, came from Guanya's lab at CMU, and the Human Plus from Stanford. I want to kind of take this, use this as an excuse to discuss some of the limitations from our stuff and maybe highlight some of the differences. From a very high level, I'd argue, SLoMo was the problem we're trying to tackle is how we can leverage existing diverse data that make them useful for robot learning, or policy optimization, whatever you want to call it. And the high level, the end goal for these motion to humanoid motion transfer projects have been thinking about how we can make teleoperation much more accessible, so we can use this as a stepping stone to collect more data and start this robot data flywheel. Hopefully this gives you some perspective into some of the design decisions that we make. From the vision perspective, we're taking very much a general purpose object reconstruction algorithm. We can throw like a cat, dog, horse, as anything human, anything with a torso and 4 legs. We can essentially reconstruct for you, as opposed to a specialized human pose estimation algorithm that's more dialed. And we're using kind of physics to regularize this reconstruction algorithm, as opposed to pre-labeled mocap data. I think in general, these works typically use the 40-hour human motion mocap data set to pre-train the pose estimation algorithm. And what the trade-offs there is that our stuff takes hours offline, and if you have some offline data you can pre-train, you can do real-time pose estimation pretty reliably. And on the control side, I'll argue this is maybe a little bit less important. We are kind of very on brand doing model predictive control as opposed to reinforcement learning from the other groups. We have to, due to some of the computational limitations, we're doing a reduced order model instead of a full order simulation you can do with reinforcement learning. The feature and the bug there is that we're able to use basically essentially the same model to control both a quadruped and a humanoid. In RL case, you train a specialized policy. But you can also say, this is actually not that big of a deal because simulation is so cheap these days. You can just train a different policy for a different robot. So takeaways here is that we did the first work on turning RGB videos into Lego robot control. I think what I don't emphasize enough when I give these talks is that I think pretty sure we're still the only pipeline that can generalize to different robots and different object morphologies in the vision step. And the key insight there is that we're using physics to regularize the reconstruction problem, as opposed to pre-labeled offline, just specifically labeled human data. In the rest of the talk, I'll be discussing how we were thinking about leverage GPUs to accelerate real-time robot control, move away from the simplified robot models into potentially, ideally whole body nonlinear models. This is a paper co-led with my collaborator Arun and co-authored with Swami, Kevin, and Zach. To maybe broadly motivate this a little bit. Numerical optimization is literally everywhere in robotics. What I mean by numerical optimization is that I want to find some decision variable x that minimizes the cost function c of x and subject to some constraint g of x greater or equal to 0. If this is too abstract, let me give you a couple of examples. The first one, robot motion planning is an optimization problem. Here's the first-person view of the Alice robot actively, taking in the perception data and planning out where it's going to place its feet in the future to finish this parkour course without falling down. And the second one is pretty interesting. State estimation is optimization problem. Here the robot is taking in sensor data from RGB cameras, presumably, and body IMUs and joint encoders. It's asking the question, where am I most likely to be? Third one, it's my personal favorite. I don't think it gets talked about enough. Simulation turns out is an optimization problem. I'm using Dojo as an example here, but all your favorite simulators, Gazebo, Majoko, all that. It turns out even in the RL case, the simulation sample that you take is a solution to an optimization problem. And the last one, this is also super common. We had an MSR talk earlier this morning on inverse kinematics. You have some end effector pose that you want to track with your robot. You want to back out the joint angles. This is also an optimization problem. And at the core of all of these things is something called a quadratic program, or QP, which means that your cost function is quadratic with respect to your decision variable x, and your constraints are linear. It turns out many MPC problems that we care about, and mostly going to talk about today, can be written in this form. So we want to solve this problem really, really fast. The first part of a quadratic program is a cost function that's quadratic. In this unconstrained case, this is twice differentiable everywhere. And to find the minima for this thing is trivial. I can simply set the gradient equal to 0 and compute the optimum, the global optimum value by solving a single linear system. And if I have some constraint g of x greater or equal to h, that tells me, my feasible region is in the green here. But the local optima I computed earlier is outside this feasible region, so I have to do something clever to fix that. And one way to kind of think about this is that we've added indicator function that adds no additional cost when we're inside the feasible region, and there's infinite cost everywhere else. And this new cost function with the original quadratic costs and the indicator function is no longer differentiable. And fundamentally, is the different ways to solve this quadratic program boils down to how you approximate this non-differentiable cost function into something that actually can be optimized. And there are classically two ways to do this. They're called the barrier and the penalty methods. In the barrier case, we're putting a log barrier around the constraint. In this case, my decision variable x are only defined inside the feasible region, which is why sometimes this is called an interior point method. And my central path parameter kappa controls how closely I'm approximating the non-differentiable cost function. In the penalty case, we have no costs inside the feasible region. We add a quadratic cost everywhere else. And as the rho approaches infinity, we also kind of from the outside approach the original non-differentiable cost function. And the way you solve these things in general is that you start from relaxed approximation, find the root, using root finding problem, find the minimum of that thing, and then warm start the next solve, and you can crank up rho or decrease kappa and solve the next problem until you're happy with your solution. And in both of these cases, the solution to the root finding problem is that the gradient of the new cost, the approximated cost function, equal to 0, and you do Newton's method on this. And the computational bottleneck, right? You have to invert the Hessian of your approximated cost function, and this is in general O of n cubed. If you think about this in the MPC context, my decision variables are states and controls. For high-dimensional MPC problems, if I want to predict over a longer horizon, n gets into the thousands really, really easily, and cubing that gets really scary. Especially if you want to compute these things in real time. And what makes the thing even worse that these things are generally, CPU-friendly processes, and are CPU bound. It's really hard to parallelize. If you look at the recent trends in computing over the last, let's say, 15, 20 years, the clock frequency actually has not gone up, which is kind of interesting. The single-threaded performance went up by less than order of magnitude, which is somewhat promising, but not that good. The most of the computation gains actually come from increased parallelization from larger number of cores. So when we're designing algorithms today, it's really important that we think about how we can leverage this increased number of parallelization in modern computing. Perhaps somewhat unsurprisingly, is also the rising interest in machine learning also kind of correlated with increased parallelization over the last, let's say, 10, 15, 20 years. And the core of the fundamental building block for machine learning is something called a neural network. Computationally, it essentially takes in some input vector V, multiplied by some weight matrix W, and add a bias vector B. These are all element-wise operations, right? These are element-wise mixture vector products and vector additions. And in the add-in, you have an element-wise nonlinear activation function. So these things are all very GPU-friendly, very easily parallelizable. And the challenge now becomes, how can we solve a quadratic problem? These things are so important to robotics, and so we desperately want to accelerate. How can we solve these problems with just GPU-friendly operations so we can leverage these, better compute in 2024? We found a way to do this. I'm going to first introduce, it's called an alternating direction method of multipliers, or the VMM. That's actually just a slight modification to the penalty method I talked about earlier. This is the quadratic program that we saw earlier. The first thing I'm going to do is introduce a splitting variable z, and set the equality constraint g of x equal to z, and I'm going to push. All I'm doing is pushing the inequality constraint into the splitting variable by setting z greater or equal to h. What this does now is now I can put this is green, it's just a little bit hard to see. I'm going to put my equality constraint in my cost function with a penalty term rho. And I'm going to solve, the way I'm going to solve this is by alternating between updating over x and updating over z. That's why it's called the alternating direction method multipliers. And in the x update, I can throw out all the terms from the original optimization problem with the z term, and all that's left is just the unconstrained optimization problem over x. And the solution to this, like we discussed a couple of slides ago, is just a single linear system solve. And updating minimization over z is a little bit interesting. Again, we've tossed out all the terms that has x in it. And look at this for a second. All we're doing here is that we want to keep z as close to g of x as possible while making sure z is greater or equal to h. And this is essentially just a projection onto the constraint manifold. And this is already looking irritatingly similar to the rectified linear function that we talked about in the neural network case. So we want to take this entire, right? But this is updating over z is very GPU friendly. But the linear system solve for updating x is still CPU friendly. So what I'm going to do is now I'm going to pre-compute this matrix inverse offline. And in the online setting, all I'm doing are matrix vector products, which now are GPU friendly. I'm going to skip over some boring algebra. And so the final result for the ADMM update for my primal variable x and splitting variable z are I'm just simply taking x and z from the previous iteration, multiplied by some weight matrix w and adding a vector b, and in the end have a nonlinear activation or nonlinear clamping for the z updates. Questions? And the final ReLU-QP algorithm is simply just starting from initial guesses for x and z. We're going to run through all the pre-computed iterations for w's and b's until we reach some optimal value. Mostly until now, we've really ignored talking about the penalty term rho. Turns out we do have to adapt to rho to get good practical convergence rates, especially if you want to do these things online. So what we do in the pre-computed case, we pre-compute the w's and b's for a bunch of different rows, geometrically scaled between, let's say, 1e minus 6 to 1e positive 6. But the good news is in the MPC setting, we generally converge to really just only needing 1 or 2 rows. So you can probably just toss out the rest because you can warm start these things really well. So that's all for the algorithm. Let's look at some of the results. Here we're benchmarking solving random quadratic programs ranging from 10 decision variables to 2,000 decision variables. We have both equality and inequality constraints in these things. And for now, we're solving to coarse tolerances. So 1e minus 3, that's terminate the algorithm when the residual is lower than 1e minus 3. For the smaller problem, we're benchmarking, by the way, against OSQP and ProxQP, which are basically, I would argue, maybe state-of-the-art CPU-based solvers. And for smaller problems, ReLU-QP, which runs on the GPU, is dominated by kernel overhead on the GPU. And for larger problems, ReLU-QP gets dominated by the matrix vector products on the CPU. On the GPU, which is much faster than linear system solve, which OSQP and ProxQP has to do on the GPU. And we're on the high end, we're about 40 times faster at the 2,000 decision variables. When we're solving to tighter tolerances, it's mostly the same story. We're about 30 times faster at the high end. And finally, the problem we actually care about are the MPC problems. Here we're generating random dynamical systems, so A and B matrices, and computing the MPC policy for these systems. When we do that for control dimensions ranging between 10 and 50, that doesn't mean anything to you. For a spot robot, generally you have 12 degrees of freedom, 12 joints. If you put an arm on it, you're much closer to 20. And humanoid robots generally can be anywhere between 20 to 40 degrees of freedoms. And especially more recent ones, if you put the dexterous fingers and all that stuff in there, you can easily push the control dimensions into the 40s and 50s. All that to say is that these are actually the control dimensions we care about, at least for today. You're faster everywhere and about 10 times faster on the high end when we have 50 dimensions. Finally, we have a couple of actual robot examples. In this case, we're perturbing an Atlas robot under control limits. This problem has 58. This system has 58 states and 29 controls. And we're able to stabilize the system at up to 2.6 kilohertz. And the MPC horizon reaches about half a second, which is about 20 times faster than the CPU solvers, and still solve this problem at 1.3 kilohertz. Yeah, go ahead.
is this a apple-to-apple comparison with OSQP? Especially, I guess, this is a LTV system, your linearized dynamics, your W and B are probably function state. So, right, we do formulations, your W and B are probably function robot states, right? So my question is.
What do you
is
mean a
this-
function of state? They don't change on
So it's
the,
LTI system.
this is an LTI system.
Okay.
Yeah, we're solving the LTI MPC system. Yeah.
Okay, so this is like fixed AB matrix.
Yeah, we're fixing A and B.
So, okay, so question is, if it's LTV system, right?
Yeah.
So you linearize some linear
Right.
system.
Yeah.
So do you need to, how do you compute the W and B matrix?
We can only do this for LTI systems.
I see.
Yeah.
I see.
Well, more on that later, maybe.
So I guess the reason asking those questions, I think OSQP, the.
Well, I'm solving the same problem with OSQP.
Yeah, but I guess part of the reason why it's fast, which is amazing, is you cannot pre-compute the structure and encode that to the ReLU network, right? Which is, I like it a lot. And right, so I'm trying to understand the gain of this is from, part of it is of course from GPU, but how much is from you have a smarter reformulation of the.
We're actually solving the same, but this is basically apples to apples to OSQP. Actually, we're essentially, taking OSQP and just pre-computing the inverses. That's actually.
Yeah, I'm just trying to understand how much of the gain is from GPU versus the CPU, how much of the gain is from different formulation to solve the same problem. I get it's the same problem, but yeah.
I don't think it's a different formulation.
What do you mean by different?
Yeah, I guess what do you mean by different formulation?
Different formulation means you not. I guess there are. I mean, the exact operations are a little different, rather. I mean, the numbers of, for example, like typically, like it's like the Foucault-Tiemann matrix acceleration paper, right? If you have more matrix multiplication, the GPU is faster.
Yeah,
More inversion or like this.
Yeah, sure. Yeah, sure.
But I don't think in this level they're same. Otherwise, why is faster? Right?
Pretty much like.
Yeah, it's
Literally the same.
I think what Guanya is trying to ask that is, like, there are two components here. One is substituting the backsolve.
Yeah, sure. Yeah. That I get.
Second is moving it to the GPU, and he's trying to understand what the trade-off.
Yeah, so-
This is with, you've also done the pre-computation for OSQP, right, on the CPU?
No, so this is just running OSQP. But what I'm also doing here is I'm running the least number of iterations that actually stabilize the system. So I'm not really solving too many more iterations than I need to solve this task.
OSQP here is not factorizing every time.
OSQP is not factorized.
That's right, that's what I mean. It's
Yeah.
like pre-factorized.
Right, but yeah,
So that is.
we're not checking residuals for OSQP either. Like OSQP only refactorize when you're checking the residuals. I'm pretty sure, yeah. All we're doing here is like, we're warm starting the problem, and we're only timing the MPC solves. So we're yeah, go ahead.
Yeah, as I said, they pre-factorize for CPU, we pre-invert for GPU, but we're not doing pre-computation first.
That's
That's
good.
not offline.
And the OSQP case, every time you update your row, you've pre-factorized again,
I see.
which is, it slows it down a little bit, but we're just
But not
solving.
none of it.
Yeah, this is not, I don't think these are in these numbers.
Gotcha.
So these are mostly,
Fair as possible.
it's, yeah.
Yeah, I get it. Makes
We
sense.
have like maybe some minor implementation detail that's not quite, yeah.
You have a lookup table for WB or.
Yeah, I think there are tricks. We can, discuss this in more later.
Yeah.
Yeah, no, thanks for the questions. And so the final example that we have is stay stuck in ARM to a quadruped, solving this pickup task. This example has 52 states, 32 controls, and we're adding a little bit more complicated constraints with linearized friction cone and pinned feet constraints in addition to the torque limits that we had earlier. And we're still able to solve this problem at 800 Hertz, or about 2.6 times faster than the CPU solvers. We're not, quite, an order of magnitude faster because there's actually the additional constraints introduce a lot of sparsity in the problem that we can't really take advantage of in the GPU case. We're only doing dense linear algebra. The limitation here, going back to the QP again, that here, as soon as we do the pre-computation, the matrix part of the problem are fixed. So Q and G, I can't really update. It's annoying if I want to do general nonlinear optimization solves. It's hard. So as you update these things, you have to pre-compute again. The good news is I can update the vector parts of the problem all day long, which turns out if in the MPC case, the reference trajectory show up on that side. So we discussed this earlier already, right? You can't update, you need some lookup tables and store all the A and B matrices, or in this case, W and B for all your for all the different linearizations. In the future work, the first train of thought is how to generalize this to nonlinear systems. The first thing to obviously try is can we solve, instead of pre-computation, can we solve these things, these linear systems efficiently on the GPU? Turns out that's pretty hard. Everyone spent plenty of painful hours working on these things. The second one, kind of going on kind of opposite line of thinking, right? The one of the insights from Tiny MPC earlier this year is that these dynamics of linearizations are surprisingly have probably a larger basin of an operation than people might expect. So I think this might be, especially if we can solve these linear MPC problems at kilohertz rays, it's probably fair to question, do we actually need nonlinear? Do we actually have to solve the nonlinear problem for dynamic walking? And the third one, we've been thinking about, we discussed today a lot on CPU, the trade-offs between using CPUs and GPUs, and my computer, the computer I'm running on this presentation on, has a shared memory architecture where you can use GPUs and CPUs at the same time without thinking about the data sharing overhead. So I think it would be really important to think about optimization solvers that actually can take advantage of these novel computer architectures. And finally, I think there are some interesting connections between solving optimization problems and deep learning. We teased a little bit with the rectified linear function activation today. Be really interesting to explore other forms of activation functions, or perhaps maybe directly learning the W's and B's instead of pre-computing them from models. And the takeaways here is that right here we're solving a quadratic program with only GPU-friendly operations online. The price we're paying is that we're doing a little bit more pre-computation beforehand. We demonstrate the usefulness for some MPC problems, some more legit than others, and we open source our implementations on GitHub, ReluQPy and ReluQP.jl, implemented in standard machine learning libraries like PyTorch and Flux. So kind of maybe wrap this up a little bit. We started from this as a cartoon example. We wanted our robots to learn on experts and be able to do whole body control in real time. We did some of those things. We were able to, started thinking about learning motion primitives from casual videos. And in a limited capacity, we're able to do whole body MPC with the help from a GPU. I think what's interesting to think about in the future, and what we kind of danced around, didn't really tackle directly in this thesis, is thinking about seriously thinking about contact. I think right now it seems like in the simulation, people seem to be generating these simulation samples really, really fast, and you can generate these things at large scale. But I think what's missing, I think, is a stable and informative gradients and how to compute these gradients at scale that can really accelerate a lot of the downstream tasks that we discussed: planning, control, deep learning, and even some of the vision cases. I keep talking to Gengshan, and Gengshan wants me to build Dojo on the GPU that can start. And I keep telling him I really want to do this. I just, hopefully we can figure that out. Hopefully we can figure that out during my PhD, I'd say. So with that, I want to thank all my collaborators, Shuo, Arun. I wrote a lot of papers with Swami, is also here. Thanks for, and Gengshan also collaborated a ton. And thanks, Kevin, Simon, and Taylor, and Mac from Stanford, Xian and Zixin, a couple of master students I got to overlap with during my time here, and obviously Deva and Zach, the senior advisors on my projects. And with that, I want to thank my all the lab members. A lot of them are here today. What? Oh yeah, this was whitewater rafting from. Yeah, this is Ohio Pile and RoboProm or whatever. And with that, I'll take. And with that, I think I'll